Awesome, thank you. So, what I want to talk today with everybody is three big reasons why machine learning code is not like regular software. And that's a big reason why I've seen a lot of very good software companies fail with their machine learning systems. So, first, a little bit of an introduction. My name is Conrado Miranda. I'm the CTO here at Verta, and as a little bit of background, I have a PhD on optimization and decision making, and I have led efforts back at Twitter and at NVIDIA to democratize data science access, facilitating data scientists to use the platform and consume all the data and create new models, but also enforcing the quality via CI/CD practices for ensuring that all the models that we shipped were the best models that we could and did not have any glaring issues. We decided to build the system now at Verta, which follows the same principles and the same philosophy, so that we don't have to go and build one at a time for one company at a time. We can just build one and have multiple different people benefit from it. It is a machine learning platform, and we're fully running on Kubernetes, which means that we can run essentially anywhere. We have deployments on premise, we have deployments on the cloud, our clouds, or our customers. So I believe everybody here today would agree that the future is intelligent. We see from applications from inside your house, like a smart robot that knows where to get some garbage, or YouTube or Gmail autocomplete, which is one of my favorite features. Just be able to write emails fast with all the content that I need. And even applications like in the power grid. And more companies are understanding that machine learning can benefit their decision making, and machine learning can really empower them to be very data driven and make very smart decisions. But at the same time, the companies are realizing that when you start to talk with enterprises, the reality is unfortunately a little bit different. The state of the art of enterprise AI and machine learning, it is surprisingly behind the curve in terms like when you compare with the state of the art that we read from like big companies. Unless your company has been spending millions of dollars on these efforts for 5+ years, you are gonna identify that there are many gaps in those companies. So there is no standardization of the model development, there's no central repository, there is no self-service for operating models. People cannot understand what's running production, and most of the time you end up with one-off solutions, which for IT is very critical not to happen. So here we have two quotes from our partners where they had faced significant challenges. And both of these companies are actually very advanced software companies, which begs the question, what happened to them that they could not translate all of their knowledge about software into the machine learning space? And from having seen this multiple times across the years and now partner with multiple companies that face this challenge, I believe the main issue is that we have misaligned expectations. We expect machine learning systems to behave very similarly to how software behaves. And that is fundamentally not the case. So the three main reasons that I'm going to touch today is first, creating a model is not the same as writing an application. Then once the model is created, consuming the model, it's not the same as just importing a library. And finally, now that you have a model that you can use, debugging it, it's not the same as debugging software, unfortunately. So let's talk about the first. When you think about an application, we might be talking about a library or a service that you're writing or even a CLI. And the usual operation process is I'm gonna get my feature request. I'm going to plan that feature. I'm going to design, I'm going to implement, test, and maintain. For simplicity, I'm not considering here the operations part and the monitoring of that, which are complicated parts on themselves. But think about the development piece. We have to do this cycle for every single feature that we develop. But it is the engineer that sits down and executes each one of these steps with their team. There is a human that plans, then designs the system, implements the system, writes the tests, and then maintains it. When it comes to machine learning, we are actually one step removed. I like to describe machine learning for folks that are not too familiar with it as essentially you have to write two pieces of software. You need to write a teacher or your optimization system plus the architecture of the neural net. So this could be what optimizer you're using, what kind of data processing you're using, which kind of architecture you're using. And again, this software that you write. So for every new thing that you want to add to the teacher, you need to plan, design, implement, and maintain. And then you also have a tester where depending on what data that you have and what metrics you care about, it's going to help you identify what to do to evaluate a machine learning model. So the idea of the tester is to tell you how good the model that you have is. So on the tester, again, it's software that some human needs to write. They need to plan, design, implement, test, and maintain every single feature that we do. Once you have these two pieces, you can actually iterate with them. You start with a model, then you pass it to the teacher, you test what is the quality of that resulting model, then you continue improving the quality, and you move on. You can go on this cycle for essentially forever. It's up to someone to decide what is the rule that's going to make the system stop and decides that whatever we have today is enough. So a big part of the challenge here is that you don't have a human actually writing the model. You don't have a human that is able to understand what is the model and what it's doing. And more importantly, the model is the feature that you carry in the end. Both the teacher and the tests, your training algorithms and your data processing are just mechanisms to get to the model. At the end of the day, they actually don't matter. What matters is the model itself. So instead of you writing the feature, you're guiding the computer to write the feature for you. And when you consider that, you start to encounter a few issues. The first being that your tests grow. When we think about the tester approach, we have essentially each point on my dataset is one test case that my model needs to pass. And in the beginning, that's usually fine. I can create a model, it passes all my tests, and everything's dainty. Now my data continues to increase. What happens? I go from 1,000 samples to 1,000,000 samples to 1,000,000,000 samples. And as I do that, it essentially becomes a problem of having more and more test cases. And we're not going to be able to pass them all anymore. You cannot depend on individual analysis to understand why hundreds of the billion test cases that you have not passed. You just start depends on metrics to verify the correct behavior of the system. So we tend to use aggregate metrics, where the most common approach is get a metric for each one of the samples, then average and get that end behavior. But the challenge there is that it is actually very easy to end up with very misleading metrics because your metric needs to correspond to what you want your model to do. But many times that's not very feasible. As an example, back at Twitter, we wanted our users to be engaged on the platform. But there is no metric for engagement. We have metrics at the system level that tells us how much people are using the platform, how much people are discussing on the platform, but there is no metric that I can put as a probability distribution of the user being engaged. So I need to now create proxies and hope that those proxies map out to what I want and do that in an aggregated level. Which, when it comes from software engineering, you say, oh, my code is going to have 80% coverage and I'm happy with that. A lot of software engineers are going to say that you're crazy. But that's essentially what we need to do here. We're not going to be perfect, and the metrics that we're going to get are not necessarily the metrics that we care about. So that requires a lot of care to think about what are you doing, how you're doing it, to make sure that whatever metrics you end up deciding really corresponds with what you want, and it can be analyzed in aggregate because you're not going to have the time to evaluate every single failure by yourself. Another interesting aspect is you get more teams involved because machine learning models, they are usually not the end, they're the beginning. You might have a model that is going to produce some information that might be missing for some users. And then that information is going to be fed to a different model. And that model is going to be interpreted by human on their analysis. And the analysis from the human is going to influence other machine models that we're going to develop inside the company. So each one of these steps of iterating with a feature that you don't really understand as a team escalates because not only you don't understand, but now the people that are providing you the feature also don't understand, and you need to build on top of this house of cards. And it is not impossible to understand what the model is doing and making sure that all these best practices for model development to ensure quality are correct. But if you just go for the usual DevOps practice, you're gonna fail because they were not built for the scale and the approximate behavior that machine learning represents. It is just, we have never had to worry about scenarios where we have a billion tests on our system and we know that some of them are not going to pass. Many teams will not ship a software that it's not passing tests. Now imagine this propagating all across different dependencies and different teams, and those models not having the right behavior, and you having to understand where that information is coming from. Which brings us to the second part of the problem, where consuming models, it is not the same as just importing a library. When it comes to software engineering, we thankfully have sat down into semantic versioning as the usual approach. I imagine most people here are going to be very familiar with semantic versioning, but as a quick refresher, every version of a library or a package, it comes with three numbers. The major version, where I'm going to represent breaking changes. My API is going to be breaking. You can expect things not to work between multiple major versions. Then we have minor versions, where we are adding new features. We are maybe adding a new functionality or extending something that's available, but we're not breaking the API. Whatever expectations I had on the version 20, I can still rely on them for the version 21. And then we have patch when it comes to bug fixes and hot fixes and just minor adjustments on a previous released version. And this is essential for us to be able to do software engineering. We depend on our libraries not breaking. We need that every single day. Otherwise, you're going to go crazy. But what about machine learning models? We unfortunately know that two models are not the same. You can start with the same teacher, the same algorithm to train the models. You can use the same tester, the same metrics that you're going to evaluate the model. And it is extremely unlikely that your whole pipeline is 100% reproducible, which means that if I run the same code multiple times, I'm going to end up with different models. And not only I'm going to end up with different models, maybe for all the metrics that I'm using, they look about the same. So here I have an example of an accuracy curve for the multiple samples on my data set. And if I compute my metric, those two models look like they behave about the same. But just looking at the distribution, we know they're behaving very differently. So whoever depends on the model behavior now is going to be broken, because my values used to be from 0.5 to 0.8. Now they are going from 0.2 to 0.9. And not only that, for each one of the samples, I'm going to end up with a different prediction. So even without any code change, we cannot guarantee that two versions are not going to break between them. So the API now, when it comes to machine learning, it is more than just the structure of the API, where I have some methods and I have some arguments, some types. It also involves what's the data going through that API. If my data going through the API changes, that is an API breakage. Even though the signature might look exactly the same, the model is different, which means that things will be different. And that's very frequently overlooked. Many times people create those models and they end up running on different machines between training and production systems. And when they evaluate the model, they get different results, they get different metrics, and they're not able to understand why. Because in software engineering, we have had a pursuit for reproducible software. The same software, when I compile it again, it should give me the same answer. It is something that whole frameworks have been built for. But machine learning is not there yet. So understanding that even adding a small feature might change the behavior of the system. And as an example, this is from one of our partners. They are an insurance company, and they are evaluating driver quality. So you install an application on your phone, and you give them permission to measure how well you're driving, and that influences how much of a premium you're paying. When they're filing with regulators, they need to tell that they are using a metric of driving quality, and someone is a good driver, let's say if it is above 0.7. Now they file that, it takes months, takes thousands of dollars to file. What happens if you have a new model? What happens if that model now, good drivers should have a value of 0.5? You cannot just go and refile that. First, because it takes way too much time. You need to continue developing your models and shipping fast. And it costs a lot of money. You don't want to be paying this every single time that you change your model. So throughout the model development ecosystem, you need to know the constraints that in the end, your model needs to satisfy 0.7 being the threshold for good driving and below that for bad driving. No matter what you do, no matter how good the model is that you just created, that is a functional constraint of the system. And that is not the kind of constraint that really is common on software engineering practice, unfortunately. And besides just that, the metric at the end of the model and the values coming out of the model, we all know here that machine learning models are very different in terms of how they consume resource. If you tell me that you have a service that is consuming 12 cores, 20 gigabytes on a machine, and it takes 200 milliseconds to respond, I bet every system engineer is going to tell you that you're crazy, that you should not be doing that. But when it comes to a complex model, that is actually reasonable. If you have a very complicated computer vision plus some NLP application, that might end up being what is actually necessary to run that model. And then you start to have to balance between latency and utilization, because the lower the utilization, the more you can optimize the latency, but then you're paying a lot of money, potentially including GPUs, which are not cheap. And more complex models might even have more considerations. For example, we can quantize the model, or we can prune the model, or I can use a specialized framework to run inference faster. So there is a whole ecosystem just about getting those models to run in a way that is compatible with their system requirements. And of course, all of that besides just the usual software challenge that exists out there. Because at the end of the day, this is still software that we're running. So all of these needs to kept in mind as you're developing your models that are going to be consumed by other applications or when you're consuming those models. But not every software is perfect. I would dare to say no software is. So debugging, unfortunately, it is not as easy as well. So I don't know if a lot of people here have used PrintsPDB, the Python debugger. It is an amazing tool. If you have not seen it before, take a look. Essentially, it allows you to have some Python code and step through and print multiple things. You might have seen that on your VS Code or your PyCharm. They have plugins for that. So I have here an example where I get an X and I get a Y, then I do a sum. And I can print the value of each one of these. I can step through. I can really understand what this code is doing and how it's doing. I can stop and analyze, which is fantastic. Like, this is a game changer for software development. But now when it comes to machine learning, although you're still running just a piece of code, at the end of the day, when you get your input, you end up with like a big array of numbers and you don't know necessarily what that means. And you get your prediction, and again, same problem. You end up with an array of numbers, and what the heck does these numbers actually mean? And I can say, oh yes, my Y is my prediction. Okay, what does these predictions mean? Like, is this the right behavior that I was expecting? Is this the wrong behavior? Just printing these values and stepping from them, it is not enough. So depending on the application area, there are ways for you to interpret. So for instance, word vectors, you can do all the algebra of word vectors, or you can like sum or take a difference and evaluate near vectors. Or if you have intermediary data, for instance, neuron activation, that's just something that we're figuring out as an industry, how to debug, how to understand what's going on there. And all of these are still areas of research. So even the most advanced techniques, they will take a while to be robust enough to be relied upon for production, the same way that we did for the regular debugger. And that's very much a shame. It is very hard to debug machine learning applications, as I imagine a lot of the people here know that for a fact by their own experience. So what does this mean for us? We need to understand how things change together. And no application is built from a single binary, a single library. And when it comes to software engineering, we have defined these traces. And the whole idea of traces is for each one of the calls that happens, I'm gonna track them down, I'm gonna add some metadata, and this is gonna be amazing. I can just leverage that, which is actually pretty great. This is a fantastic debugging tool for real world software engineering where you cannot necessarily stop everything and debug through the debugger. You cannot just step through the code. But how do I do this for machine learning? We still don't know. There is just way too much data and way too high dimensionality for me to be able to build something that's as intuitive as a simple timeline with a couple of log lines. I need to understand my requests, not only one request at a time, but in aggregate. Maybe I don't really care if one of the requests have a little bit of bad data, because maybe that's the data that should be there. It just looks a little bit weird. But if all of my requests have a bad data, then I want to know about. So the statistical nature of data science and machine learning is really a game changer because correctness is no longer absolute. Correctness is relative, and it's relative to the samples that you have and the sample size. Sample size of 1 is probably not going to give you a lot of signal. Okay, great, Conrado. You pointed out all the things that are wrong with machine learning. That's not software engineering. Now I'm depressed and I don't know what to do. Yeah, I'm not here to cause desperation for anybody. There are things that you can do about it. The first one is improve communication. Machine learning projects usually have such a new kind of requirements and a new ecosystem that a lot of teams forget that they need to communicate more to be able to explain what are the constraints and the guarantees that we need. So first, really understand the stability guarantees that the product needs. We tend to place more constraints that we actually need to operate the products. And let the team have some wiggle room. If your constraint is good driving is 0.7, let the team go crazy on everything else. Because the more flexibility you give the team, the better the models that they can create without having to artificially place constraints. Make sure to communicate and align expectations throughout the model lifecycle, from the people helping collect the data, annotate the data, train the models, deploy the models in production, create the model dependencies. Everybody should be on the same page about what problem we're solving, how we're solving it, and what stabilities we have. And accept there is no silver bullet. There is no one solution that's going to work for every single data science problem on every single company. There will be trade-offs to be made, and they're going to be hard trade-offs. They're not going to be easy, but you have to make them. If you just postpone, you're not going to be doing your company any favor. And of course, create on top of DevOps. Your company probably already has a very good infrastructure that is built for software practice. Leverage that. Just because DevOps is not enough doesn't mean that it is not a good base for you to really create solid machine learning robust infrastructure. So understand what are the good practices, and also why that's not enough. Connect with the multiple teams and across timelines. Many times when we're doing machine learning projects, we are talking about projects that can take months to be done between collecting the data, annotating the data, training a model, running an A/B test, and deploying to production. So not only you need to connect with the multiple teams that exist at a moment in time, make sure that you're connecting with past and future selves. Leave notes for your own team to look into the future. And accept that you're going to be dealing with more information than a human can comprehend. And that's okay. That's why we were building machine learning to make these decisions instead of humans. Just make sure that whatever solution you end up building, you build with that in mind. And thank you, everybody. You have here my email and my Twitter. Feel free to reach out. I love talking about this topic. I've been talking about this for over a decade now, and I just love every single moment of it.